So I'm Edward Amston. I'm going to be talking about an introduction to functional reactive programming. So there'll be a very short introduction, talk some about the history of functional reactive programming, the distinction between the two main classes of functional reactive programming, classic and signal function, how we implement functional reactive programming, some of the applications that it has been applied to, and some of the work that's ongoing with functional reactive programming. All right, so let's get started. So our motivation for all this, when we're writing real programs, TM, we have to deal with the real world, TM. And in this real world, we have to deal with time, and it tends to produce inputs that we can't predict. So we can't have the whole input to our program when we start to run. That's not a realistic assumption for applications programming. So our usual solution to this is we write event loops in our programs and put callbacks in to handle the different sorts of things we expect might come along. So the motivating question here is, well, instead of doing it that way, can we extend some of the benefits of functional programming to handling these characteristics of the world? So jumping right in, FRP has these two basic abstractions. There's one that, depending on which paper you're reading, will be called behaviors or signals. They're the same thing, and they're just functions of time. So they're a mapping from a point in time to a value. And we also have events, which are temporal sequences of discrete values. So they do not map every point in time to a value, but rather just certain points in time. And we tend to call each of the individual values occurrences and the whole set of values an event. So if we have a language that's an FRP language, it also has to include a way of sort of altering or replacing a part of the program in response to an event. That's how the program is reactive. And so we might reify these abstractions directly in an FRP language, or we might use them as the basis for other abstractions, but they all have to be present for it to be an FRP language. So some of the people involved in FRP, as we start to talk about the history, probably the single most involved person has been Connell Elliott, who's previously at Microsoft Research. It's sort of hard to tell exactly what he's doing right now, but he... Freelancing. Yes. So he pushes a lot for denotational semantics, not just in FRP, but in functional programming in general. Has worked a lot on the implementation of functional reactive programming as well. Paul Hudak was the other person on the original FRP paper, which we'll get to in a minute. He's at Yale University, and his big focus currently is applications of FRP to multimedia. So he has a system called Utopia, which is a FRP system for multimedia. And previously he wrote a book called The Haskell School of Expression, which was sort of along those same lines. Anthony Courtney was a student at Yale, graduated in 2004. He was one of the primary creators of what we call arrowized FRP, and he also created an embedding of FRP in Java. And he also turns up in various other places in the FRP literature. Henrik Nielsen worked with Paul Hudak at Yale and is now at the University of Nottingham, still working on FRP. He created the system called Yampa, which is similar to the AFRP system, but it's just sort of optimized. And Neil Sculthorpe was a PhD student of his who just started a postdoc at the University of Kansas. And Sculthorpe's PhD thesis was the N-area FRP system. So starting from the very beginning, functional reactive animation was the sort of original FRP paper. This was Connell Elliott and Paul Hudak. And this is the paper where behaviors and events were sort of proposed as the basic abstractions. And the sort of implementation of the system was just something to evaluate these behaviors that were carrying a picture and sort of show you an animation. And there are ways to get, I think, just mouse and keyboard in as input. So you had a very basic sort of interactive animation setup. The next paper is genuinely functional user interfaces. This was Elliott again, and then Anthony Courtney. And the motivation here was to try to have a declarative specification of GUIs based on FRP. So if you're familiar with the arrow abstraction in Haskell, this moved from taking signals and events directly as the abstractions, and instead having an arrow between signals and events, or the idea of signal functions. So signal functions themselves are reactive, so the signal functions are what get replaced in response to events. And they take events and signals as inputs and outputs. Push-pull functional reactive programming was the first paper, first of all, to really give any attempt at formal denotational semantics for functional reactive programming. There was another paper that sort of attempted to answer the question of whether the sort of sampling exercise for continuous signals was sound, but didn't really give a complete denotational treatment. So this paper did, and then used it to prove the soundness of a transformation into a particular normal form, which then essentially let him lift all of the reactivity to the top level, so you had sequences of non-reactive behaviors that were carried in event streams, and then he could evaluate these with concurrent threads. So this gave him a couple of advantages in that every previous system had sort of spun and polled to see if an event had occurred, which is obviously quite inefficient, and also introduces sampling latency for events, so he was able to avoid these. But since it's using threads, it's not a purely functional implementation, and there's a very, very nasty sort of clutch built in for merging to event streams as well. This paper was the paper that described the Yampa system. The title is quite a mouthful, but essentially what it comes down to is GADTs enabled him to sort of describe the internal structure of signal functions so they could be pattern matched at runtime and dynamically optimized. And then this paper, it was Neil Sculthorpe's PhD thesis. He actually embedded arrowized FRP in AGDA, and this introduced the idea of signal vectors where, instead of in the Haskell arrow implementation, where any value really can be an input to your arrow. And so the abstraction that came out of that was just, well, you have one signal that may carry embedded events as option values. This actually had a description of combinations of signals and events as inputs and outputs for signal functions. And my master's thesis, which I will hopefully be defending very soon back at the Rochester Institute of Technology, brings in Connell's idea of a push-pull signal function system, or a push-pull FRP system, into the idea of signal function systems. So I use Sculthorpe's idea of signal vectors, and this allows me to evaluate events in that push-based manner where I'm not spinning and pulling for events, but rather just sort of sitting there and waiting for them to occur. So now we'll get more in depth into this distinction that I've already touched on between classic and signal function FRP. So just an overview, if you're ever browsing through the FRP systems, this is sort of a list of which ones fit into which category. FRAN is the original sort of FRP system, functional reactive animation. Connell-Elliott's system, Reactive, is what was described in his push-pull paper. Reactive Banana is sort of the state-of-the-art, funnily enough, system. Elm is another classic FRP system that's implemented in JavaScript, and Frappe is one that's implemented in Java. So in terms of signal function FRP, you have Fruit, which is functional reactive user interface toolkit, AFRP, which is sort of a generalization of that system into a general FRP system, Yampa, which, as I mentioned, is an optimized AFRP, N-area FRP is Neil Sculthorpe's embedding in AGDA, and Time Flies is my new push-based signal function FRP system. So with classic FRP, as I mentioned, these events and behaviors are first-class abstractions. These are the things you program with. These are the things you compose to write your program. The downside to this is that all of your primitive events and behaviors have to be provided by the system. There are sort of workarounds for this, for allowing users to construct their own, but essentially you have to have a primitive event or behavior already provided by the system for every sort of input you might want to process. This does not generalize very well. But you construct programs by composing events, and you can lift functions and values to behavior, so it is possible to have a behavior carrying a pure function and then apply that to another behavior, so behaviors do generally form an applicable functor. In contrast, signal function FRP, we have signal functions as the first class abstraction. So you don't actually manipulate events and signals directly, but you manipulate transformers of them and compose those, and those are also the reactive components, so these are what can be replaced in response to events. And you have what's called an evaluation interface, which is what you hand the signal function to actually let it run, and what takes care of the work of actually going and getting the inputs and then handling the outputs of your signal function. And you construct programs by lifting functions to signal functions and then composing these with other signal functions. So all this is a very nice abstraction. How do we go about implementing it? Well, for classic FRP, the easiest way to implement a behavior obviously would just be as a function from time to values, but that turns out to be very inefficient because you essentially have to keep around the whole history of the behavior. So we actually implement them as functions from time to a sample value and a new behavior, and assume we're always going to be sampling them monotonically, so we'll never go back and sample an earlier time. So this permits a behavior to sort of throw away its history and avoid what we call time-space leaks, where as time goes on, you keep using more and more memory because you're keeping around history that you'll never use. Events are generally just represented as a lazy list. Some implementations like Reactive use something more complex, but either way, you have to have some reified form of no, there's not an event yet. Signal function FRP, we represent signal functions as one or more continuations which take in the time and some input and produce, again, an output and a new signal function. In my system, I actually split out each signal function actually has two continuations. One is for a time and signal update, and the other is for an event update. And this is how I get that push-based event behavior, where I can evaluate the timed component separately from the sort of immediately responsive event component. These continuations, as I said, they produce output updates to the signal or output event occurrences, and they also yield a replacement signal function. So that was a very brief idea of how we actually implement these things. As far as the applications of functional reactive programming go, things that have been implemented so far, there's been a few sort of animation things in games. Fran had a bunch of examples that all amounted to variations on the bouncing ball theme. Yampa has been used to implement two games. There's a clone of Space Invaders that was implemented in Yampa. There's also a 3D first-person shooter that was implemented mostly in Yampa, although not entirely, and that's called Frag. There's one, this all sounds very nice for writing audio applications, but so far only one person's gotten that to work, and that project is called Yampa Sync. There have been numerous applications to robotics, sort of as like summer school sorts of things, but the only actual project working on applying this to robotics is FROB. And that, I believe, is also one of Connell Elliott's projects. As far as work that's still going on the semantics side, like I said, we've been given a semantics for classic FRP. Unfortunately, there's almost no work on the formal semantics of signal function FRP. This is something that bugs me, and I sort of intend to fix. In the original signal function FRP paper, the genuinely functional user interfaces paper, there's a two-paragraph sort of informal semantics that signals are functions from time to a value, and signal transformers are functions between signals semantically, which is very unsatisfying. So something I'd like to see, can we build I have a notion of how we might, sort of a toehold, how we might make a category theoretic semantics for signal function FRP. And the big question to be answered there is the switch construct, which is what lets you replace a signal or a signal function with another one based on an event, is sort of temporal composition. It's saying, build me a signal function which acts as this first one for some period of time and this other one for the rest of the time. Now that time's indeterminate because we don't know beforehand when that event is going to occur, but this is still a notion of composition in my mind. And then implementation and performance. We expect push-based event handling to yield a performance increase, certainly on the latency side and also on sort of the side of resource utilization. There's also been some work at dynamic optimizations, but I think there's a lot more work to be done there. Yampa sort of showed an ad hoc framework for that, where you can sort of plug in ad hoc optimizations and sort of hope they all work together. I think there could be a lot more work done that way. There's also been exactly one static optimization of FRP to my knowledge. It's called causal commutative arrows. And essentially, if you have a non-reactive signal function, so something that doesn't have a switch or any reaction to an event inside it, but it does have feedback, which is another thing we can model, you can lift several embedded feedback loops out to one big feedback loop in a principled way. Something I've been talking about with Brian has been staged code generation for FRP. So can we essentially build the FRP system, run it for a while, and then if we have a something that looks like it's stable, can we JIT it and compile faster code and apply more optimizations to it? And can we build parallelism into FRP as well and not have to run our entire FRP implementation on one core? So in summary, so our motivation, again, we want to have a good way of reacting to the real world. We have behaviors or signals and events as abstractions for this. We implement with continuations. You have a function that says, here's what happens, here's the value that I got based on this time update, and here's the function for what I will do next. And applications, really, you could apply this to anything that could be modeled as a reactive program, which in my mind is anything other than the simplest math problem program really could be modeled in this way. So with that, are there any questions? Yes.
So like these behaviors, I assume they have outputs also. Like, do they trigger other events, or do they like
behaviors are just values?
Okay. Or so then the handlers then, or whatever is actually like reacting.
Okay. So the way this works is you're composing values to build a system. So behaviors, you eventually you're evaluating this value with something, right?
Okay.
To actually, you're evaluating the behavior that's got a picture and actually drawing that picture somewhere.
Would you maybe like draw a picture of what one of these programs looks like or something?
Sure. So let's spin the camera around this way. So for classic FRP, because that seemed to be where
that one's kind of crowded.
Okay. Because that seemed to be what Eric's question was motivated by. You might have this basic sort of box that's an event value that's your keyboard, right? And you might apply you might map a function over this for key presses to get sort of let's say you want to get left and right key presses. So this would be, you would actually be sort of events are a functor, right? So they're essentially just a lazy list of occurrences coming in, so you can map over them. So you would map a function that just pulls out the left and right key presses or filter. And then you would wrap all this, perhaps you compose this with a function that says, we might have a construct to move something based on these key presses, and the other part of this would be something that outputs a circle picture. So this is sort of this is one of the examples talked about in a lot of the FRP systems, where you map a function over an event to get a new event, and then you have something that's producing a primitive signal that's a picture, right? So you've just lifted a constant value of a picture into a signal. And then you have a function that constructs a behavior based on these left and right events, and this circle, and gives you a circle that's sort of displaced from the origin based on how you've moved.
So is there like some sort of a flow through this then? Like from the keyboard to the left-right function to the move?
Yeah, sort of coming out. This is actually why I don't like the classic FRP abstraction so much, because you sort of want to think about things that way, right? And this is why we have signal function FRP, where instead of sort of wrapping these things around each other, I would actually be saying the keyboard, it would turn into function composition, right? Where I just say I'm expecting the keyboard as input, and you'll supply that through the evaluation interval. So I'm expecting key presses as input. But then I feed that into the left and right function, whose output gets fed into the move function, but parallel with that, the output of the constant circle function is getting fed into the move function.
I think people would be good with the type signatures and or the code.
Yeah,
that would be fantastic.
So if I just had this would be event key press, right? And would be can everybody see this?
In the chair. Thanks.
All right, and then you have and So all you're doing is applying, in the classic FRP setting, all you're doing is applying functions to values. And then the neat thing comes in how we would construct move, which is we actually have something called switch B, which has this type signature. In the simplest formulation, it has it's called switch B because we say behaviors, but I've been writing signal, and they're the same thing. So it takes in an initial signal, and it acts as that signal up until the first occurrence happens in this event stream. It doesn't replace it with every occurrence in this event stream, but just the first one, and then it acts as that signal or behavior from then on. So this is how we would build move, as we would, and the other thing is, as I mentioned, behaviors are applicative functors, so I could just lift functions from the circle and time to a displaced circle and switch between those functions based on a switch B, and that would be my move. And then that would turn into something that takes in whatever picture I'm moving, and based on the events coming in, moves it left or right. So this is a sort of value compositional model. In single function FRP, switch instead looks like.
Hold on, quick question.
Yeah.
So, could you write a switch-free version of this moving circle controlled by the keyboard if you have hold or something for that event stream?
You could, but hold is just sort of a wrapper around switch.
Oh, I guess hold and integrate.
You need an explicit time value somewhere, but time is just behavior double or whatever your real number setup is. And it's just a very simple behavior. So yes, you could, and you might want to do it that way, but hold is just one use of switch. So in single function FRP, our switch looks like we have a Well, let's do it with signal vectors. We need more space. That's over here. So, switch takes a signal function which has some vector of inputs and some vector of outputs with a with an event carrying a new signal function, and take this to just the signal function with that input and output. So what you wind up with is you act as this first signal function, its left output, which can be an arbitrary vector of signals and events, but then its right output is consumed by switch, and as soon as it produces its first occurrence, it is essentially replacing itself with saying, okay, I'm done, here's the thing to replace me with. So you can build...
Maybe explain the two arguments of SF?
Yeah, so SF has a vector of inputs and a vector of outputs. And so if you want to sort of linearly compose signal functions, the output of one has to match the input of the other. But these are the signals and events that are the input to the signal function, and the signals and events that are the output. Clear as mud? Any other questions? Back.
So, like the point of FRP, to distill it down to at least part of it, is to like be able to interact with the real world and events in some kind of state in a reasonable way, right?
Yes.
So that seems like also the domain of like substructural type systems and that kind of thing. And in particular, I'm thinking of substructural logic programming. Seems like kind of a natural fit for this kind of model. Do you know, has there been any kind of push to look at things from one of those kind of perspectives?
There's one tiny little piece that just came out earlier this year. The only thing I'm aware of doing anything sort of fancy in the types of FRP is that your question, sort of? There's almost
Could
no.
you explain the connection to so-called substructural types?
Yeah.
I mean, so this is ill-formed question, I guess, in the sense that I don't know if there is like a substructural type system that can do it like this, but I do know that often when you do use substructural types, I guess like in Rust with affine types, for example, that does have to do with the state of a program in the sense that only one thread or whatever can have access to this.
Right. Okay.
And that pattern of a thing that takes in like one event or whatever and returns you like a new event and a new handler for it or something. That's very much the kind of style.
Right. So just in case there's any confusion, that's the implementation. That's how, if we want to write an FRP system, that's how we implement all this actually happening. All of these things actually happening through time. But that is very definitively not the interface that we expose to the user. Okay. The user sees things in classic FRP, the user has primitive values of type signal or event or functions between them and composes these to build his program.
Right,
So, yes.
It seems like, though, a substructural type system might be really good at making sure you don't hold old values of signals around.
Right, and that's been...
make sure that things go one way so you don't have space leaks.
Yes, and in classic FRP, that's been their really, really big sort of bugaboo, is that they have to explicitly not keep their history around. In signal function FRP, we don't have this problem because we're using transformers and we just sort of look at everything point-wise and explicitly keep state around if we need it.
Right, and you could tell with an affine type system whether you need to keep state around or not.
Right, so it'd be very helpful on the side of implementing FRP systems, I'm sure, but I'm not sure it provides any advantage for the sort of the interface to FRP.
Well, is the work that you were talking about, Neil Krishnaswamy's paper in Popple from this year? Because I do know it did talk about space leaks. I don't remember how they did it. I remember they did some fancy type
No,
stuff.
the work I was referring to was actually, now that I've heard what you guys are talking about, it's not really the same thing at all. But there's but it's the only work I'm aware of actually doing anything fancy with the types for FRP, and it was essentially a Curry-Howard isomorphism between the types of classic FRP, just essentially as they're expressed in a standard parametric type system, and a particular form of temporal logic.
Okay.
I think this was Alan Jeffries
Okay.
that did this.
I don't, he might have been one of the authors on the
Okay.
paper I'm thinking of.
Okay.
But it was cool. They had some kind of, I think it was temporal and some other stuff, and they used it to get rid of space leaks, and it was
Right.
neat. I saw the talk. I don't remember
Okay.
anything about it.
Yeah. So in particular, I'm very fond of the signal function model because it lets you do things like this, where you sort of wrapped up a very generic reactive behavior inside something that just has an input and output interface. So it's compositional because I can transform both the input and output, so I'm not restricted to building my construct around a particular type of input. So, but B, again, it lets me wrap up. There might be a switch hidden somewhere down in there, but I don't have to know about how the reactive behavior is implemented.
Yeah.
So you essentially are just building bigger and bigger boxes of things.
So this was high-order functional reactive programming in bounded space by Neil Krishnaswamy, Nick.
No, I'm not familiar with that paper.
Okay. I don't know.
Inbound. So this sounds like an embedded sort of. There's occasionally efforts to move FRP to the embedded space by saying, hey, we can do this in. There was a lot of, right after FRP came out, there was a huge flurry of papers on bounded time and bounded space implementations of FRP because people wanted to program embedded systems in this way.
This was a Popple paper from this year, right?
Yeah.
Okay.
Yeah, but maybe we can talk about this offline, but
Yeah.
it seems like there might be applications for this in substructural logic programming, and I would be interested in
Okay.
hashing that out somewhere.
Yes.
So, it seems like here you have a pretty strong assumption of causality, right? That you have.
You absolutely.
There is a DAG, so you couldn't do this over, say, space.
You absolutely have a assumption of causality. This is sort of implied in the signal function model, where, like I said, you don't evaluate in terms of, like, you're not applying behaviors to time. Like I said, behaviors are
Right.
just you have signal transformers, and you just start up with a signal transformer and start feeding it input and time updates and saying it's stepping, right? In classic FRP, they have to enforce causality because you can actually apply this behavior to the current time minus 1 second, right? But if you tried to apply it to the current time plus 1 second, then suddenly you have a problem, right? So yes, you have to have an assumption of causality to make this whole thing work.
Okay.
Yes.
The paper that presented the denotational semantics introduces also the idea of the space-time leak very, very specifically in those semantics, saying they were having problems removing that. Early work on FROG, they introduced the idea of, well, we'll just pretend we never look into the past farther than we know we will. But they also said that's inconsistent with the semantics. Are you aware of any work that has come up since then to try and
Not in the
fix that disconnect?
Not in the academic space. I know that the reactive banana system that I mentioned, which is Heinrich Appelmus, he's currently blogging about this sort of thing, and his current solution involves, I think at last count it was up to 9 different phantom type parameters in the behavior and event types. So it's not a pretty solution at all. But he thinks he has solved it, but then is that really a solution if you have that many things flying around to keep track of things in the type system? And single function FRP just sort of neatly sidesteps this whole issue.
But you don't have a full formal semantics for it.
Exactly.
So we don't know if it's sidestepped.
We're pretty sure in practice that it is, but
Okay.
because the way a single function FRP system is implemented, like I said, you don't have anything sitting there that is a function of time, right?
Okay.
You have sort of you have functions from this incremental update to the output and the next function of incremental update, right? And that's what you have. And so if you want to keep any state around, you have to do it explicitly by dropping it into
To
that
do that
closure.
explicit forwarding kind of.
Yes.
Okay.
Yes.
Which is how they ended up solving it in the EFRP system.
Well, this is how it's solved in all FRP. They do the same thing behind the scenes in the implementation of behavior, which is what I said. That's why we don't just write behaviors as time value functions. We write them as time continuations. They do the same sort of incremental thing, but it's not as natural of a thing.
Okay.
Yes.
So I mean, your time continuation thing then, so there really is nothing that prevents you from saving the old signal functions, right? They're not like, say, monadic or something.
Right,
where you can
right,
only
right. There's
get at
nothing that
them.
prevents you from it, but you just don't.
There's no need to, basically.
There's no need to, unless you really, there are accumulator functions, but even then, you're keeping a
Right,
separate
that's still a
accumulator function.
causal
Yes.
thing.
Whereas with
It's not keeping history directly.
Yeah, whereas with a behavior, if you have a function that's explicitly time to value, that function implicitly contains the whole of its history.
Right.
So it's a question of whether it's implicitly kept around or not. And we're saying, no, you have to explicitly keep around any state that you want in signal function FRP. Other questions?
Could you give a more concrete example of the kind of dynamic optimizations that you said Yampa does?
So the really simple one is, let's say, so just notationally, this is the serial composition operator for arrows in general and signal functions in particular. But what if you have, say, so you have this sort of thing, right? There's absolutely no need for this to exist, but because this is sort of handing off continuations and incrementally updating itself, it's doing real work for no transformation of anything, right? So Yampa, and this, you would never actually write this, but if you have something that's switching, right? Something might switch from, its behavior for a while might be, say, +1. You're spitting out floats and this is a +1. But then after a while, some event comes along or some condition happens that it switches, and now it's identity. So, but you're still doing real work there. So for, like I said, for no gain. So Yampa can recognize this situation essentially by pattern matching on your whole signal function structure. If you look at the code, it's really messy because there are, the data types for signal functions turn into like 500 constructor data types.
Okay, so identity is a special constructor.
Identity is, right, and the other issue is this is not a complete optimization, because if you say, which is exactly the same thing in terms of what you expect it to do.
I'm sorry, what does that?
R is the arrow lifting function. So this lifts a pure function to whatever arrow you're using. But this will just say, hey, I have some pure function, right? It'll be the constructor for some pure function lifted to a signal function. So there's a separate signal function called identity, which acts exactly the same way, but constructs itself with a constructor that says, hey, I'm the identity function.
So you have to write your program to switch from ARR +1
to identity. Yes, and then it will get optimized way. So this is a very brittle sort of optimization, but it can be done, and that was a big breakthrough.